Okay. So I'm just gonna go ahead and open up, we're recording now, by the way. I'm gonna go ahead and open up everything. Um, so for December 1st, I've gone over this lecture a few times with you guys, but not everyone. So I think we're just gonna start from there. Brief overview of everything, and I'll send the notes afterwards so you guys have that. Um, so what what this whole new section is going to be about is just triple bonds. And there's some easy things you can do to just like kind of know everything about triple bonds. And then you can kind of use those to help you with your retrosynthesis, which is probably going to be a good portion of the final. Um, Possibly like, a couple of pages out of the exam will just be retrosynthesis that is not bonus. So we kind of, if you're aiming to get, like a 70 or higher, you probably need to know retrosynthesis, a little bit at least. So let's start with the December 1st lecture. I'm starting from the notes. Um, so kind of one thing that he's pointing out here, which is I think going to be on the final, is about the acidity of molecules. So or acidity of reactions. So reactions prefer to go to the side where it's less acidic. If you think about acidity, it's almost like instability, all right? It's like I want to give this hydrogen, so it's unstable. And if a reaction has, one side is more acidic than the other, it'll prefer to go to the side that's less acidic. Now less acidic means lower pKa, so we need to remember those terms. Um, but acidity and basicity is definitely going to be on the exam, so that's really important. Now, a quick review of acidity and basicity. The first most important thing is atom. And what this means is the atom attached um, to the hydrogen. All right. And basically, this follows the trend that we all know, right? Where it goes, acidity increases to the right and increases downwards, right? And this is primarily important, and this is secondarily important. Um, so this is just, your basic acidity, which we know from, Gen Chem. An example of something like this might be like um, OH versus NH versus SH versus FH versus IH. So, um, Destiny, why don't you tell me how you would rank these in terms of acidity?
Okay, one second. Um, so I would do IH as number most acidic.
Mm-hmm.
Then I would do wait, I don't know where S comes. Um,
S
let
in
me
the periodic table, it goes like this. There's CNOF, and S is right underneath
oh,
of
okay.
O.
So then I think I would do, would it be F next? FH? Or would it be S?
It would
H.
probably be S because
Okay.
S is more down than F.
Okay.
Because
So
that's
then,
why I said the primarily thing. Because
okay.
most important is how far down it is. Okay.
So yeah, then SH, then it would be FH for 3, and then NH, and then OH.
OH would be first.
Oh yeah, my bad.
Yeah. Um okay, perfect. Yeah. So this is how you would rank them. And that just goes by our normal trends. So we kind of already know that. Now, the thing about like going downwards, this has to do with bond length. And I'm mentioning this because it is very important. I would definitely know this before going to the final. It's important to know why acidity increases as you go down because of bond length. It's important to know why it increases as you go across because of electronegativity. Okay, so that's it. And there could be easily like a question where it's like, you know, explain why this is more acidic than that, and you would have to talk about electronegativity and bond length. Very important. Um, Second most important thing when we talk about acidity is resonance. So I don't think I spelled that right. I don't know. But anyways, so with resonance, basically what it means is that it can absorb like that negative charges can kind of like no, that double bonds can fluctuate around a molecule. So something like this, um, right, has potential for resonance back and forth between those two oxygens. Because if we examine this closely, you might remember how once we let go of that OH, that becomes O minus. So then lone pairs from here can go down, and then that would bring it up, right? That's potential for resonance. So that's probably your most common example of resonance. Um, Now, another example of resonance would be something like this, a cyclohexane, and this is the example that always confuses us. So basically or like this. So in this situation, what you do is you go ahead and if you think about that hydrogen leaving, so if you're confused about whether there's resonance or not, just draw it with the hydrogen gone. And what you'll see is that this lone pair, when it comes down, this has to move. So that's resonance as well. Okay. Now, does anyone remember that one question which he always asks and I keep forgetting what the answer is? There's one question where it's like three different cyclohexanes or two different cyclohexanes. I want to say it's exam 1, practice exam 1. I'm gonna try to go to that. And if you guys have any questions, just let me know in the chat or just say something and I have it open so I can see. So the one kind of pitfall with resonance is this. First of all, there's this one question where he says, how about this with 2 double bonds versus this with 1 double bond? And what you see here is that if I zoom in, basically when you lose your hydrogen there, you can easily form a double bond here without having to rearrange anything. So this is no resonance, right? All right. Now in this example on the right, we just showed that kind of, and in this case there will be resonance because when your lone pair tries to come down, the bond that's here is going to be forced to move. So when I look at a resonance question, I would seriously consider, you know, what's kind of happening here. Is this going to allow for resonance? Don't just like memorize anything. The last example I want to show you is an example where there's already this going on, and you might have an OH. Now in this example, oh, how this looks. In this example, you have an OH here. The hydrogen leaves, right? And you have O minus. But this lone pair just can't come down. It literally can't. Why? Because that would just break octet. There's nowhere for that double bond to go. All right. So this is kind of a lesson in the fact that it's not more double bonds is better. It's just seriously draw it out and see if there's resonance or not. Is that clear kind of? Okay. So that was the second factor. And when I'm mentioning these and I'm numbering them, it's because that is actually how they are in terms of importance. The first most important thing is the atom. So if there was resonance, but they had different like atoms, like for example, if I had um, uh, I don't know, let's say I had this versus, and let's say that this had a double bond here. Which one's more acidic? You'd have to circle this one because the first most important thing is the atom. Even though this one has resonance, it doesn't count because the atom, first of all, is worse than sulfur. So this is going to be better. All right, now let's look at the third thing. The third thing is going to be, what is it? Induction forces. So what induction forces are, they're kind of similar to resonance, but it doesn't involve double bonds moving around. It's basically about if there is some very electronegative. So what are electronegative molecules? Electronegative molecules very much love negative charges. So it's the idea that there might be some kind of electronegative atom on the molecule that helps absorb the negative charge. So an example of this is something like that, right? Where we have, maybe like an OH leaving. And we have a fluorine, which is the most electronegative atom on the periodic table, right? So this means that when the hydrogen leaves, the negative charge on the oxygen, you can think of it like this. It's kind of being supported by the electronegativity of the fluorine. All right. Now, what's really important about this, guys, is that it's electronegativity. Like, it's important to remember that this has to do with electronegativity. A lot of people think that, oh, they try to follow the regular trends for acidity. They try to follow the regular trends for acidity on this, but that's not true. You have to do electronegativity. So if you have, like if you have F versus I, people are like feel like doing I because they know that I is involved in being more acidic, but actually it's fluorine because fluorine is most electronegative. All right. I'll just leave that example there because it's important. Okay. Next, yeah, so I'm just going to give a few more examples of this. So this is the one thing to note about induction forces. Now, induction forces, you need to watch out for number one, the atom, where you want it to be more electronegative. All right. And the second most important thing, or not the second most important thing, but the second thing to look at is location. So closer to to basically the how can I say this? Closer to the negatively charged atom is equal to more acidic. So what this means kind of is that, as you can imagine, you know how the fluorine loves to help out with this negative charge of the oxygen. If we had an example, again, with fluorines, I'm going to make it really simple, where we have a fluorine here versus an example where the fluorine is like, I don't know, farther away here. This one would be the better acid because that fluorine is going to be able to interact with the hydrogen more closely, whereas here it's going to have less of an influence on helping with the negative charge. Okay. Any questions? All right. Inductive forces. I actually need to hurry this up because this is supposed to be a exam 3 review, not exam 1. But if you want to know more about this, just check out the video about exam 1, where I think I talk about this, or exam 2, I'm not sure which one. Now let's go on to the fourth most important thing, which is hybridization. So with hybridization, what that basically means is that SP is more acidic than SP2, which is more acidic than SP3. And you can think of this in a few different ways. You can kind of just memorize this, or you can kind of know that the higher the concentration of S, so this is 50% S is better than, in this case, it's 33% S, which is better than, in this case, 25% S. And I'm getting these from the fact that, this one, for example, is an S and then 3 Ps. So that means this is 25% S. And so you can think of them in terms of percentages, or you can think of them in terms of just, I don't know, memorizing it. But that's the basics of that. And now an example of this might be something where we have like, usually it's carbons we're talking about. So this versus, and this is looking very familiar by now, but this versus, I don't know, this, right? You look at this carbon that's going to lose a hydrogen, it has, it's sp3, and this one, sp. So this one is more acidic. That's it. Okay. Any questions? So that's the basics of acidity. Obviously, basicity is just the opposite. Now, that was just a quick reminder because that stuff is definitely going to be on the final. Now, moving on, we have reactions, right? So we have this example here I got from the review. So basically, this goes to so looking at this right here, if he asks you which direction does, or he'll probably say instead, sorry, he'll say something like are products or reactants favored? And then you would look at this and you would compare the two acids because, like I said, so basically you would just compare the two acids. So our two acids in this case are, yeah, so he won't give you the values for the acids because that's the trick. You have to figure out how strong the two acids are. So, Mubaraka, where are the two acids in this case? So there's an acid on the left side and an acid on the right side. And it's basically, oh, I forgot to add this a reversible arrow. So there's an acid, there's always going to be an acid on this side, a base on this side, and an acid on this side, a base on this side, in this question in particular. So can you identify which one's the acid on the left?
CN, the CH triple bond to CH.
Yeah. So this is our acid. And then where's the acid on the right?
NH3?
Okay. So you just have to look at which one is donating a hydrogen, because that's what an acid is. So in this case, Mubaraka just looked at this on the left side right here, or on the right side here, and she said, okay, so clearly in order to get back to this side, the carbon one has to gain a hydrogen, and it's gaining it from here. So this is the one that's donating its hydrogen to the carbon group. All right. So reaction. So now that we've identified our two acids, we need to compare the strength of these two acids. So basically, we just need to go back to our beginning principles. The first most important thing is atom. is there a difference in atom here? Destiny.
Can you repeat the question?
So I was saying which one's more acidic out of the two acids that I've circled?
Oh, probably NH3 because the N.
Right. So then we just have to draw an arrow. So our answer would just look like this. It would just be arrow towards the products and then write like a P. And that shows that you understand, or no, sorry, arrow towards the reactants because reactants are less acidic. And then basically you're telling him that you understand that this side, the acid is less acidic. So the reaction is going to favor there. All right. Next. Okay, so now we're just going to move into the meat of what we're doing today, which is triple bonds. So you guys already taken the quiz, so you kind of already know this. But so there's just a few reactions here, and I'm not going to go through the notes like really systematically. I'm just going to go off of like what I want you guys to know. So the first most important thing to understand about triple bonded carbons, which we kind of talked about up here, is that, triple bonded carbons are going to be more acidic or more willing to let go of their hydrogen than a single bonded carbon. So that gives us an interesting situation here where we can kind of remove this hydrogen and it will remain a fairly stable molecule, right? Remember how we talked about so basically it will remain pretty stable. So right? So that one on the left is more stable after removing the H. Now, what this means is that we can use this in various reactions. We can remove the hydrogen, and then we can just do different things with it, and it'll work in interesting ways. So how do we remove the hydrogen? You remove your hydrogen by taking your typical triple bond, and then you basically are going to react it with Na, NH2 over NH3. And what this is going to do is it's just going to take away that one of those hydrogens. So that hydrogen is gone and it now has a negative charge. And then, you might want to draw like your sodium, which is going to kind of hover in the solution next to those negatively charged carbons. Like a spectator ion almost. So basically, this is how you do that. And it doesn't necessarily have to be this structure in particular, just any triple bond with carbons. So you could have this, right? And we react this with NaNH2 over NH3, and that just gives us the same thing, but with a negative charge on it. So that's kind of the basics of that. Now, this negatively charged carbon is actually really useful because we can use it in two ways. We can use it to use it as a nucleophile, right? They can act as nucleophiles or bases. Now, let's go over the nucleophile, or let's go over the nucleophile example first. So what Dr. Zahn is saying here is that if it's primary, if the leaving group is primary, it'll act as a nucleophile. If it's secondary or tertiary, it'll act as a base. So primary leaving group doesn't look very clear. Primary leaving group, it acts as a nucleophile, and then secondary or tertiary leaving group acts as a base. All right. So let's go over a nucleophile example first. For the nucleophile, all we have to do is kind of have, again, like a primary leaving group. So your leaving group, from now on, we'll just use Br. But you intuitively understand that it could be anything. It could be OTS, it could be Cl, it could be water, it could be anything. But we're just going to be using BRs because that's going to make it more like uniform and convenient for you guys to see. So we basically take that triple bonded negatively charged carbon, react it with some nucleophile with a BR on it, maybe, some kind of leaving group, but it has to be primary. This is primary, right? So what this is going to give us is going to give us that structure from where it's going to be attached to this carbon. And so the mechanism for this is kind of that, the BR is carbonating, and then this would be SN2. Now, and how do we know it's SN2? Oh, you guys can hear me now? Oops, okay. How do I know this is SN2? Any volunteers? Versus SN1, maybe?
It's 1 degree.
Yeah, it's primary, and from our blue sheet, we know that, primary leaving groups always produce SN2. There's no option for that ever to be SN1. So this is SN2. Now, the one thing that I would caution about here is your carbons. So I really think that, if you're someone who doesn't do well with, counting carbons and that kind of stuff, very, very important to count your carbons because you will get points off for that. So I like to count the number that's on here. That's 1, 2, right? And then on this molecule, we have 1, 2, 3, 4 carbons. So we know that we have 2 carbons here and 4 carbons on there. So that needs 6 carbons in the end. So you have to go back. If you're one of these people who doesn't always get this right, you have to go back and you have to count 1, 2, 3, 4, 5, 6. Now you're good. Okay, must count that. I think there was one thing I wanted to say about this. So you can do dialkylation. So for dialkylation, well, let's go into something else first. So Dr. Zahn, what he might do is he might give you this, which you've already seen on the quiz. He might just give you this starting product, right? And he will do both of the steps in the same time or in the same arrow to save space. So it will be Na NH2 over NH3, and then the bottom you'll have your halide or your alkyl halide. So this kind of just saves space, and you have to be aware of this because this is the much more convenient way to do it. You don't want to have to do out this original step where it becomes a nucleophile, right? You don't want to have to do that every time. So this is so much more convenient, saves so much more space. Just do them both in one step. And so what you get is you just get the same thing. First, the carbon becomes negatively charged, then it substitutes onto those things. So again, but this is really important to know. Now let's move on to dialkylation. So this is the idea that you can add alkyl groups to both sides of because if you have this triple bond on its own like this, you can attach something. You can remove a hydrogen. I'll draw it a little differently. You can, right, it's attached to hydrogens. So you could remove a hydrogen and substitute something onto there, like a nucleophile. And then you could remove this hydrogen as well and substitute a nucleophile on, right? So there's a possibility for, if you have just a triple bond with nothing on either side, there's the possibility for 2 substitutions on either side. So we can kind of do that. We can kind of do, let's do 1. So this will be like Na NH2 over NH3. And the second one, let's just add like 2 carbons. So 2 carbons with a bromine at the end. And so then that'll give you the triple bond, and it'll have 2 carbons at one end. It doesn't really matter which end you choose. So I'm just going to go like that. Let's count our carbons to make sure. So we had 1 and 2 carbons from here. So that's 2. And then we had 1, 2 from here. So that's 2 more. So we need to count, and indeed we do have 4 carbons, right? So this works out, right? Now let's do that one more time to substitute onto the other side. So this is going to be on your retrosynthesis, really important to know. NaNH2 over NH3, and let's just do like something else different this time. Let's substitute 3 carbons on. So we have 4 carbons to begin with, and we're substituting 1, 2, 3 on. So what we need altogether is 7 carbons. So again, you can just draw your triple bond out, and you have the 2 carbons on one side, and then you have the 3 carbons on the other side, right? So we count these up. 1, 2, 3, 4, 5, 6, 7. So that's perfect. Now, one thing I want to point out though is when you're drawing triple bonds, it's important that, or it's not that important, but it's a good practice to kind of keep the lines on either side straight, because triple bonds don't have cis and trans. So you can kind of just do like this. So again, this is still just 7 carbons. 1, 2, 3, 4, 5, 6. But what I've done is I've kind of made it so that there's no cis and trans right around the triple bond. So the triple bond is like this, and then the 2 carbons on either side go flat out. Triple bonds are linear. Okay. Okay. So, I mean, that's not, it's a good thing to do. Might as well just do it. Um, the meeting's gonna end, so let's come back at let's come back at 8 o'clock, because it's gonna end in like 5 minutes from now. So let's come back at 8 o'clock. So that was an example of dialkylation, and I just wanted to bring up that point about from now on I'm gonna draw all my triple bonds flat on either side because they're gonna be linear. So let's do this now. All right. So basically what I'm trying to say here is that okay. So basically if it's a secondary or tertiary leaving group, what's going to happen is that you're going to create a base. So on your quiz, I think you guys had this, right? It was like this. Or actually, no, you guys didn't have this, but you could have this. Where he says, like, I don't know, like, here's this. What do you have to react it with in order to get it to become, or let's do it as a retrosynthesis form. What do you have to react it with in order to get it to become this? Maybe. All right. So we look at this and we're like, oh, okay, so, well, one interesting way of doing this would be to just use this as a base. There is the option of, do you guys see the 2 options here of how to do this retrosynthesis? I'll do the first option, which is what I'm aiming at here is I'm aiming at using it as a base. So first you'd want to just make this into a nucleophile. So you would do NaNH2 over NH3. And that would give you the triple bond, but now it's negative, right? Nice. Now here, I would just react it with a base, with that molecule. So you can just react it with this. And you can put a leaving group here, right? That would give you elimination. You guys see that? Because this is just acting as a base, so it's just gonna create a double bond. Now, the other option is to instead you could, but this is gonna be like a little bit more complicated, so that's why I prefer the first way. What you could do is you could go, you could substitute first. You could look at this and say, well, this is being reduced to, it could have been a triple bond that was being reduced to a double bond. You guys see this? So it could have been this, right? It could have been, oops, let me just redraw that. Could have been this before, and then it somehow reduced to a triple bond, right? So what do we know of? Like, I don't know. This is just I haven't gone over it yet, but we know of this reactant that can make a triple bond to a double bond, and it can make it trans. What is it? Destiny? What's the one that can reduce a triple bond to a trans double bond?
It could be like NaNH3 or LiNH3.
Yeah. NaNH3 or LiNH3. That basically makes a trans double bond. And then we could think to ourselves, well, then how are we going to get from here to here? That's going to be a series of substitutions. So first we're going to substitute one carbon onto the right and two carbons onto the left. So this is just, let's just go ahead and substitute our one carbon first. So Na, NH2 over NH3. And then secondly, just a single carbon with a Br on it, primary, right? So this is going to give us triple bond with one carbon attached to it. Then we can do this other step where we're going to do 1 Na, NH2. So we're just repeating it again. But this time we're going to be attaching two carbons, and that's what we're going to get. So we've attached 1, 2, we've attached 1. So the two originals plus that 3 gives us the total 6. Or no, sorry, the total. Can you guys hear me? Okay.
Yeah, I can hear you.
Okay. So I just finished talking about an example of using it as a base, and I was talking about how you could do this alternate retrosynthesis, where you kind of just like add to each side of the double bond, and then finally make it into a each side of the triple bond, and then make it into a double bond, a trans double bond. So those are your two options for that kind of synthesis. And oftentimes from now on, you guys will have multiple options. And even so much as there's actually no better answer sometimes, and you just have to come up with something that works, and then you should get most of the credit or all of it. But one thing is that if you end up with this retrosynthesis that is super, super long, you're probably doing something wrong. Or there's something better. And you might not get the full credit if it's like very, very long and complicated. So the other thing I wanted to point out about retrosynthesis is that let's say you just really can't figure it out, but something is a minor product, you could just go ahead and use that and get most of the credit, or at least some of it. But it's better to find something that uses major products only. So we went into elimination. Again, elimination is going to be with secondary or tertiary leaving groups. So a mechanism for this, I'll just draw it out real quick. So basically we go, Na, NH2 over NH3. This gives us, and then what this can do is it can react with, like this. And so what happens here is that bromine protonates, and then this comes in and attacks the carbon that the bromine protonated from. So what you get is you just get that original structure, and then it's attached to a carbon, which is triple bond attached to this. Okay. So, now we've talked about how to kind of work with double bonds as nucleophiles and bases, which is really the only thing to do there. But the other thing we can talk about is kind of how to form triple bonds, how to break away triple bonds, all that kind of stuff. So that's a second topic. So how to form triple bonds. The only way that we know of, at least now, to form triple bonds is to have a dihalide. What this means is that it has to have two halogens on it. So it has to be some kind of alkyl group that has two halogens. So halogens come in two different forms. Dihalogens come in two different forms. So we have the example where they are vicinal, and we have the example where they are geminal. So this is the vicinal example. Let me spell that. Okay. So the vicinal example basically is that you have one hydrogen here, one hydrogen here, or you could put it in terms of the bromines, one bromine here, one bromine here, whatever way you like it. Geminal has to have two hydrogens on the beta carbon. So basically, the reaction for these is exactly the same, whether it's geminal or vicinal. So you just do 3 moles of NaNH2 with NH3, which is familiar by now, and then also H2O. And what this is going to do is it's just going to make a triple bond, or I said I would stop doing that now, a triple bond between where the two halides had been. And the other example is geminal, so just 1, 3 Na, NH2 over NH3, and H2O. So this is just going to form a triple bond towards the carbon that has the two hydrogens on it. So it gives us the same product, really. So this is just to show you that, you don't have to, it doesn't have to look any particular kind of way. You just need two bromines, and they have to be vicinal or geminal, but either way you can produce a triple bond like that. Some examples where you can't produce a triple bond, I don't really know if you'll ask this, but something like this, you can't produce a triple bond here because basically you can't form a triple bond going in this direction because that would violate octet for this carbon, right? So what we're going to get is no reaction because you can't get this, right? This is not going to work. All right. So now let's move in. So that's how to form triple bonds, and that's like the only way that we kind of know of. Now we're going to talk about how to break triple bonds. And so the first one is how to go from triple to single, which you will need to do sometimes. And in this situation, you just take your triple bond. All right, let's say it looks like this. And you react it with 2 moles of H2 and PT, or PD, or nickel, or RH. And so basically, this is just going to give you, this whole thing is gone, and now you just have a single bond. All right. Make sure that your carbons match up. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, this is extra. So, yeah, so that's how to go from triple to single. But when we go from triple to double, we face this issue of, is it going to be cis or trans? And that's where we have two options. Let's do cis first. So the cis option involves Lindlar. So we have, let's just do the same example again. So it's like this, and we get Lindlar. And then basically what happens is that it's cis now. So it goes like that. All right, so that has become a triple bond, a double bond, and it's cis. Now, if we want to go from triple to double but trans, we have to use a dissolving metal like Destiny mentioned earlier. And our dissolving metal can be lithium or or sodium. So it can be NaNH3, or it can be LiNH3. Either of these would work. Right? And basically that's just going to give us the same thing, but it's going to be trans. And there's a double bond there. Any questions?
I have a question.
Mhm.
Earlier, you know how we did like the geminal one, and then you said no reaction. Yeah. Is it possible maybe that we get, instead of a triple bond, a double bond? Because we have NH, the NH2 thing, or would it just be no reaction?
I would write. I would probably write no reaction.
Okay.
But you could ask him if it's possible. I'm sure it is possible that we form a double bond. But obviously, the optimal way to form a double bond in this case would be with a base, like a strong base, like an oxygen, or something like that.
All right.
So I would ask him, but I would say no reaction if I saw this on an exam, because I know that he's aiming at this triple bond situation, but it's not going to happen. But that's an interesting question. So yeah, that would be a good question to ask him, but I'm pretty sure it won't show up like that. Or I mean, it might. So yeah, just ask. If he says anything, let me know. Just email me his answer. So we talked about Lindlar, dissolving metals, whatever. Now what else is there? Okay, so now we're going to talk about, there's other ways to go from triple to double, right? And those include mark and anti-mark. So basically, let's review what mark and anti-mark do. So anti-mark and mark, they basically take a double bond, and they basically, when you add like an HBr, for example, it will kind of, let's make this better. Okay, so it'll put a hydrogen in place with the most hydrogen. So in mark, H goes to more H, to the place with the most H's, and S negative, whatever that might be, will go to the place with less H, right? And if you need a review of this, just watch the video about exam 2. So, but what this essentially ends up doing is taking away that double bond. So in adding a bromine here and a hydrogen here, this double bond can no longer exist on that bond, right? Because you can't keep a double bond there and somehow still have a bromine on there, because that violates octet. So the idea behind mark and anti-mark is that you add two things to each side of a double bond to remove that pi bond. So same thing with triple bonds. We're just going to start off like this, right? And reacting this with HBr, what it's going to do, it's going to change this, first of all, to a double bond. So it's not like it goes straight to a single bond, but it does remove one of the pi bonds, right? Because every time you add a Br here and a hydrogen here, you have to take away one of the pi bonds. So this is now an acceptable molecule. And what happens here is that you're basically going to have, what do you call it? You're basically going to have, oh wait, we didn't make this. Let's make it different a little bit. Let's make it like this, so that there is a difference in terms of hydrogens, right? So here we have 1 hydrogen, and here we have 0 hydrogens, right? So the hydrogen is going to go to the place with the most hydrogens, so it's going to end up on the tip right there, and then bromine is going to be on the other side of that, and there's going to be a double bond. Now, something interesting is that we can do this again. We can do this one more time. So react it with another HBr, and what this gives us is basically, again, the hydrogen is going to go to the place with the most hydrogens, bromine is going to go to the place with the least hydrogens. So we have that original bromine there, and we've added another bromine here. And then there's 2 hydrogens here. And obviously the double bonds are gone. So now we have no pi bonds, and we have 2 bromines substituted on. We substituted first 1 bromine and then another bromine. All right, any questions about this? Did you guys notice how this is geminal? Something we talked about? So my tip in general is that antimark produces vicinal and mark produces geminal. Wait, let's do another example. Let's do antimark now. So triple bond HBr H2O2, and then what's going to happen is that it's going to form a double bond, but the bromine went to the place with the most hydrogens, and the hydrogen went to the other one. One more time. And we get, again, we're going to get something else this time, right? Since this place had 0 hydrogens, and this place had 1 hydrogen, it's going to prefer, wait, no, never mind. That's not true. This place has 1 and that place has 1. So where will it go? It could go to either one now. Wait, no, this one has 2 hydrogens. What am I talking about? Okay. No, this is 1. Wow. Okay, yeah. So there's 1 hydrogen on either side. So what does this mean? You could go to either one. So your bromine could, so you could end up with geminal, you could end up with, you could end up with vicinal, you could end up with geminal. Because when there's no preference for either side, then it's just random, and you'll end up probably with both. All right. So my point here is that just do them out, kind of, and see. But one thing that I want to point out, though, is that if you have a uniform triple bond to start off with, so, and just ignore everything I said above and focus on this now, because you can look at the notes later and figure it out. But if we have a triple bond that's uniform in terms of like hydrogens, so it has no hydrogens, right? 0 hydrogens on this side and 0 hydrogens on this side, right? So you react this with mark twice. So let's do the first reaction with mark. So the first time you react it with mark, HBr, it's going to be like this. Double bond, and since there's 0 hydrogens on both sides, it's going to go to either one. So it'll just be a Br right here, right? And then, or R on the other side. Either would have been fine. Now let's do it one more time. Now in this round, so in this first round, it could have gone to either side, right? But in this round, it is going to prefer to go to a certain place because this one has 1 hydrogen and this one has 0 hydrogens. So hydrogen is going to go to place with the least hydrogens. So what you're going to get is you're going to get a bromine here, and the second bromine has attacked the other carbon. So, or no, sorry, this is, oh my God, this is mark. I was thinking anti-mark. So we're basically gonna get 2 bromines on the same one. Is everyone following? I just need to check that everyone's following because I might have confused you. Do you see how you get 2 bromines on the same carbon? Okay. So, basically, the thing that I was trying to point out is let's do an anti-mark example, right? So this was a mark. So, mark plus anti-mark with same hydrogen, basically. That's what I'm trying to illustrate here. So you're doing the mark example first. Let's do an anti-mark example, HBr, H2O2. So what happens is that, again, it's just going to go to either side, So whatever. Let's say, no, let's just, for the sake of consistency, let's make it go here first. So again, we're looking at this. It has 0 hydrogens and 0 hydrogens. So next, we're going to do this one more time. HBr, H2O2. And what's going to happen here is that there is going to be a preference, because there's usually a preference on the second round, even if there wasn't one on the first round. So this one has, again, 0 hydrogens. This one has 1 hydrogen. So the Br is going to prefer to go to the most hydrogens, however you want to think about it. We're going to end up with 1 Br here and 1 Br here. So something that, like, I noticed that you guys, if you're the kind of person who likes to memorize certain things about organic chemistry, you can just kind of memorize that if it starts out with uniform hydrogens on either side of a triple bond, mark is going to make it a geminal to either side, and anti-mark is going to make it vicinal. And knowing this is kind of helpful for your retrosynthesis, because if you see something that ends up with, and you guys had this on your, actually, I don't know if you guys had this on the quiz. Was this on the quiz, quiz 7? Did you guys end up with a vicinal dihalide? Yeah, you did, right? Yeah. So on your quiz, you had a vicinal dihalide in the end. So most of you knew that this had to be from a triple bond right before it that underwent anti-mark twice. Right? So you might say 2 moles right before that. So that's just like an easy thing to do that'll save you so much time, you know? You don't have to figure out how you're going to do twice and then whatever. You can just do it both in the same step, and it makes your whole retrosynthesis much easier. All right. Next, oh yeah, so this one was also on the quiz. Enols and ketones. So this reaction is pretty interesting. Basically, it involves a triple bond. And what happens to this triple bond is that it undergoes this reaction with H2O, H2SO4, and HgSO4. And so what happens is that you get an enol, which means that you just it's like something we did before. I can't remember the exact steps. I think it was in double bonds we did something like this. Double bond, and then it was B2H6 and H2O2. Am I right? Because I haven't reviewed this stuff yet, but I think I remember this reaction. This is it, right? This is the one where you get an OH. Let's make that different. You get an OH going to the place with the most hydrogens. So an OH would be here, and a hydrogen would be here. So it's very similar to this, and then it adds an OH and an H. And so basically you're gonna have your 1, 2, 3, 4. You're gonna have a double bond, because we're basically removing one double bond by adding an OH and an H. So we're going to have an OH on one side and an H on the other side. And basically this is the enol form. And then you can turn this will spontaneously go to a ketone form where it's basically a double bonded O. That's what a ketone is. A ketone is a double bonded O. So it's important to know the names of these, because oftentimes when he asks them on the exams, he will say, like, I want you to draw the ketone in this box and the enol in this box, because it's kind of like 2 products. It's 2 products, but the ketone is more stable, so that's important to know. All right. Yeah. So I think that's it. So the ketone to enol thing is pretty important. Are we getting this? Does this make sense? Okay. And basically you just take that OH and make it double bonded. That obviously removes the double bond from on the carbon next to it, because it can't, you know, remain there with octet. Okay, and then here's some more quick reactions, which is like we already kind of intuitively know this stuff, but it's good to learn it. So triple bond reacting with Br2, and this is similar to a double bond reacting with Br2. Just you get a Br here and a Br here. And one thing I would say about the final is it's going to be a little tricky because you kind of have to balance your knowledge of triple bonds with double bonds on the same exam. So that's why I'm kind of doing examples with double bonds right beneath them so that you guys can see how that works. You can see the relationships. And so with a double bond, it's the exact same thing as well. Oops, there's supposed to be a double bond there. So you add 2 BRs in the same go, removing 1 pi bond. It's the same. Ozonolysis is actually a little different, but still very similar. So ozonolysis in triple bonds is, I think that this was pretty interesting, something that I talked to, I believe it might have been, Destiny, was that you who was asking about ozonolysis last time?
Yeah, that was me.
Yeah. So something that I talked to Destiny about was about how cyclic versus acyclic ozonolysis. So if you have like a cyclic ozonolysis, so ozonolysis involves, having, let's just do your typical, cyclohexane example. So we're going to start off with a double bond to jog our memory, and then we're going to do a triple bond. So these both are cyclic examples. Notice that. So we break the double bond in half here, and it's reacting with ozonolysis, right? So O3 and then H2O2. So basically what happens is you can just draw the same exact molecule. I've kind of simplified my approach now because it'll make it easier for you guys to understand. But where that double bond had been, just draw a double bonded oxygen, which we now know that this is called a ketone, right? So that's interesting. Learning a little bit more every day. But basically, you break that double bond in half and add 2 double bonded oxygens to either side. But before I used to talk about how to unfurl it, make it look nicer, but you don't really need to do any of that. This would be a totally acceptable answer. Now, with a triple bond, you can kind of break that in half as well when it reacts with ozonolysis. And so what happens here is that just draw the same structure out and the double bonded oxygens. That part remains the same. The only difference is that you're going to get an OH on the other side of that ketone. So you can compare these two things directly. In this case, you have an OH coming as well, and that's the only difference between triple bonds and double bonds in ozonolysis. Now, the thing that I was kind of talking to her about, and this is like, again, like I do not like memorizing anything for organic chemistry, but if you do, this is interesting to think about because I think it's intuitive. You do it and then you see that this has become acyclic. But sometimes people, don't really see it. But so I really I kind of am embracing this whole, memorization aid type thing since it helps a lot of people. But basically, if it's cyclic, it will become acyclic after ozonolysis. So you notice that both of these examples are acyclic in that they're not rings anymore, they're actually chains. I mean, I kept them in the shape of a ring a little bit, but they're not attached to each other on the sides, so they're straight, they're flat. And I'll redraw them flat the way that they are, just so that you can see that. It's basically 6 carbons, and there's an oxygen at either side. That's if you unfurl it. But it's acyclic because it's not, even though I might be drawing it in the shape of a ring, it's not really a ring anymore. Now, this one is the same thing, just the 6 carbons and double bonded oxygen, double bonded oxygen. Just make sure you add your OH here because we had started out with a triple bond. All right, that's it. Now, let's talk about acyclic ozonolysis. So, in acyclic ozonolysis, what happens is that you're going to go from acyclic to 2 products. And let's go over an example of this. So let's just do our typical double bond, ozonolysis. And what happens is that we break this in half. So all we get is we get the one side of it with a double bond and the other side of it with a double bond. And that's good enough. And then let's do a triple bond example. So this is our triple bond reacting with O3 and H2O2. And then just break that in half. And then you have a carbon with a double bonded O. Let me keep the orientation the same. Actually, no, that's weird. So a carbon with a double bonded O and then OH on the other side, and another carbon with a double bonded O and an OH on that side. So basically, what do you call it? It's like you've made two products, you know? You have the one product and you have the one product and the second product. Again, one product, second product. So acyclics makes two products. And remember I mentioned this and I'll say it again, the only way we know of currently, I'm pretty sure, the only way that we currently know of to break off carbons is ozonolysis, because if you think about it, in this acyclic example, you're reducing the number of carbons. We went from 4 carbons on the left to 2 carbons on the right in each product. So if you see something where their amount of carbons has decreased, you should know that it's ozonolysis, most likely. Are we cool with that? Because I don't think we know of any other way. We might learn one by the end of the semester, or like I haven't reviewed December 3rd yet, but I'm pretty sure this is the only way we know of breaking off carbons. So if you look at your first product, I'm talking about retrosynthesis right now. You look at your first product, you look at your second product. I really like that example I did the other day. What was it? I think maybe if we start off with like a triple, no, I'll make it a little bit more complicated. Let's say I give you this, and my product is this. So as soon as you see an O and H combination, this is only for Orgo 1, because in Orgo 2 you'll know some other stuff. But as soon as you see the O and H combination, you should know that this came from ozonolysis of a triple bond, right? So you can just draw like a triple bond right before that. And that can be attached to, how many carbons do we have here? We have 1, 2, 3, 4, 5. So we need 5 carbons on the one side of it. So this is 1. So that's 2, 3, 4, 5. 2, 3, 4, 5. So we need 5 carbons on one side of it because it's going to make 2 products. It doesn't really matter what's on the other side. Your 2 products aren't always the exact same thing. If you do ozonolysis with this, you're going to get, you know, a very small thing with a double bonded O and an OH, right? So it's just going to look like this with the 1 carbon in the middle, right? So it doesn't really matter what's on your left. If you're doing retrosynthesis, you don't need to worry about that. But we know that if we see that OH combination, we know it must have been ozonolysis. And then from here, we can kind of see that maybe forming a triple bond and then substituting carbons on. That's kind of like the pattern we've been doing. So how to form a triple bond here, 3 moles of Na, NH2, NH3, and H2O. Let me add my numbers here. And then that's just going to give us triple bond with, you know, regular CHs. And then just do that first, make it into a nucleophile. So Na, don't forget this step, Na, NH2, NH3, make it into a nucleophile. And then secondly, attach it to, we have 2 carbons here, right? And we have 1, 2, 3, 4, 5, 6 carbons here, right? So we need to add how many? 4, right? So 1, 2, 3, 4, and then a primary bromine or something. And that'll give us so that's the optimal pathway for this retrosynthesis. All right. So when you see this, it's ozonolysis. All right. But similarly, if you see less carbons in the reaction in the end than in the beginning, you also know that was ozonolysis. So if I gave you something like this, and this will just help you practice a little bit. Let's say I gave you this, and I also, and the end product was, well, looking at this, you've lost a good amount of carbons, right? You had 1, 2, 3, 4, 5, 6, 7. So we started off with 7 carbons, and now we only have 3. So we can look at this and see, oh, maybe we can form a triple bond and then do ozonolysis. You get the idea. You can try this one on your own if you're looking at the notes later, and you can send me your answer, and I'll tell you if it's right or not. But I'm not going to go through it now because there's some other important stuff to cover. So let's see. Now he goes into his own retrosynthesis examples. Now I tend to give harder retrosynthesis examples. When I come up with ideas, they're harder than normal. So if you're not getting some of these, don't worry. As long as you're kind of understanding what I'm saying, learning a little bit, and then as long as you can kind of do everything he does in class, you're good. So let's choose some retrosynthesis from here, and I'll just walk you through my thought process. So, and today we're kind of just going to finish up with December, with December 1st, and then we'll do December 3rd tomorrow, or on Sunday. So he starts off with a cyclopentane, and it has a triple bond. Interesting. And I like retrosynthesis with triple bond because it tends to be a little bit more like easy to spot what's happening because there's so few reactions you need to know. So looking at this, we have a triple bond originally. Let's count our carbons. I think that's always the best thing to do. So we know there's like 5 carbons in here. There's no need to do that. Outside of that, we have 1, 2, right? And on this example, we have 1, 2 as well. And there's an OH. Now that is not an OH with a double bonded O. So this is not ozonolysis, right? So don't get confused about that. This is not an ozonolysis example. How do we know of how to add OHs? Well, there is the method of doing a triple bond with an enol, but that would still leave a double bond on. So what I'm talking about is basically if you start off with a triple bond and you react that with that whole thing that we know, H2O, H2SO4, HgSO4, right? We know that basically you're going to get a double bond with an OH on it and a hydrogen. We don't want this because there's still a double bond on that one. So let's try something else. How about we reduce it to a double bond and then make it use OH? That way that double bond would be gone, right? So let me because of the double bond, that's an issue. So let's do this coming just from a double bond because we already know how to do that from the previous exam. So we have our cyclopentane and it's just a double bond there. And we need it to be anti-marked, so the hydrogen needs to go to the place with the most hydrogens. So the best thing for this would just be the one I mentioned before, B2H6 and H2O2. And then how can we get from here to here? That's pretty simple. This is just, this looks like, it's kind of trans because this OH went trans as well. So let's just do it, I mean, or it's cis, it doesn't really matter because there's no carbon on the other side. But I'm just going to do trans. You can choose Na, NH2, NH3. No, I keep doing that. Okay. This is the one to go from, it's just NH3. NaNH3. There's no NH2, NH3. So yeah. So I'm gonna go with that one, just a dissolving metal to kind of make it become double bond. So remember we went from triple to double. We had the two options. We can do Lindlar or a dissolving metal. And I chose a dissolving metal. Questions? All right, let's do one more. Or a couple more. This one is a triple bond, and it goes to a double bonded oxygen. Now, again, I like this one because it's not ozonolysis. Why not? Can you guys tell me in the chat? Why is this? How do I know this is not ozonolysis? And I did that in the previous example. I explained why I don't think so. Well, ozonolysis does have a ketone involved, kind of. It has that double bonded O. But what's the difference here? No one's giving me the correct answer, or the most correct answer. How do I know this is not ozonolysis? Well, there is the possibility that it could be ozonolysis from a double bond, right? But we know it's not ozonolysis from a triple bond. How? What's the marker that it was ozonolysis from a triple bond? Oh, yeah. I thought you guys were saying O, and I was like, what? Yeah, so OH. So in ozonolysis from a triple bond, I had just mentioned up here, where are we? Here. I mentioned that this OH thing that you keep seeing here, this is the marker that it was ozonolysis from a triple bond. If you don't have that, that wasn't ozonolysis from a triple bond. So going back, we now know that this was not ozonolysis, I should add, from a triple bond. Right? Because this is a ketone. It has no OH involved. So, I don't know. So what do you, so, let's see. It could be, I mean, do you guys want me to go through the example where it could be ozonolysis from a double bond? Okay. So what I'm going to give you now is a super creative retrosynthesis that is only for practice. I don't really think, I don't know, there's a possibility it could come, but let's do this. Okay, so the creative version, which I'll do in blue because blue is more creative, is, and it's not even a better one. It's just good because it shows that you can think on different levels if you give this one, but I don't think you'll like it better. So don't do something like this when there's a much easier option. In retrosynthesis, you might come up with all these fun ways to make things, but you should stick to the most simple, straightforward thing that uses everything we learned in class. So here, a creative way to do this might be to think, okay, well, what if this had come from something where it had been a double bond right here, right? So this was a double bond, right? And then when you break that double bond, this carbon here is gone. So we broke it in half. And this carbon at the top is gone. Because you guys know that there's an implied carbon there, right? The CH2. So you could think to yourself, well, what if there had been a double bond up there? And then basically, let's just make it like a little bit more obvious though, because at this point you can do anything you want. So maybe we could make it like something like that. A double bond with like two like an ethyl kind of. So this with ozonolysis would give us the answer, right? because it would just break it in half and there would be a double bond O there. Because this is double, right? Double bonds don't have the OH as well. Just a double bond O and that's it. So how can we get from here to here? So I'm thinking to kind of substitute carbons, obviously, and then reduce it to a double bond. Actually, no, this would never work. Never mind. Does anyone know why this would never work? Anyone have any thoughts? Why would this never work? Okay, so because you can't substitute a triple bond onto something that is secondary. So let's say I had created this, right? This is the structure here. You can't take this, protonate the bromine, and substitute this on because with secondary or tertiary leaving groups, it has to be what? What did we discuss? These negatively charged carbons with secondary or tertiary leaving groups. It's elimination, not nuclear. Yeah, exactly. It's elimination, not substitution. And this is obvious though, because when I actually tried to go do it, I was like, oops, that's not gonna work. Because you can't put a triple bond on there. So it's not something that you even have to know. It's like intuitive that you can't substitute a triple bond onto where a secondary leaving group had been. Does that make sense? So like if I have this secondary leaving group, I can't protonate this and attach a C minus onto there, because if I do so, I would end up with this. And that doesn't make any sense, right? So it's not like something you even have to memorize. It's just, it's obvious when you try to do it that triple bonds can't substitute onto a secondary or tertiary. It's going to be way more likely to do elimination. So that's why I think that this one is completely not going to work. So I'm just going to cross it out. But I really like looking through his examples and trying to come up with more complex ways to do it, because then you basically kind of end up testing what you kind of can do, can't do, and then you come to realizations like this that you start seeing, okay, this nucleophile could never substitute with a secondary leaving group. So the best way of doing this though is when you see that double bonded O, we know that this is a ketone, right? And we already know how to go from enol to ketone. That should strike a, that's how we first learned about ketones in the enol example. So, wait, is my screen lagging again? Okay. And you guys just come back as soon as, yeah, it's lagging a little bit. But you guys just come back as soon as it kicks us out again. Okay, so basically, we know that this ketone could have come from an enol. So, basically, let's see. So we know that this would have been like this before, maybe with like a double bond here and an OH here maybe, or an H here. And then this would spontaneously become a ketone, right? So there's no need to write anything here. You don't need to write anything because it's spontaneous. How can we go from a triple bond to, oh, and this came from this. 1, 2, 3, 4, 5, 6. Yeah. So this came from that, and what did it do? It had H2O, H2SO4. If you're not remembering all this stuff right now, that's fine because we just talked about it. So there's no need to like actually know all this stuff right now. Just know by the final H2SO4. Now we need to substitute 2 groups of carbons onto this. So that's going to be like a little kind of situation where we basically have to do substitution twice. So you guys can do that, and I'll just write like SN1 and then another SN1, because there's not enough room. But I'm seeing here on the answer key that he actually did something different. He made okay, so continuing from where we had just been, basically something that he did, which would also get you like full credit, is he put the OH, but the double bond was here. So that's interesting because it eliminates that step of having to add groups to both sides of the triple bond, because this would just come from a triple bond on the end, and then it would just be like this. There's an extra carbon there. So it would just come from that. Right? And then from here, you would only have to substitute this one group on. So that takes away that step of having to do 2 steps of SN1. It's just SN1 once onto one side and you're done. So I like that. But both of these would get you full credit if you did SN1 twice or the other way. But I think that this way is superior, the red way, because basically in this example here, since this is anti-mark, right? This is anti-mark. So the OH would have had an equal like thing of going here. So that's a mistake almost, because you'd end up with this product, but also you would end up with, wow, this is so complicated. You would end up with this product as well. So I don't like the one that I did in black, because it gives you 2 products and it's not like it's not a pure reaction, right? So the best one is the one that he showed.
Hey Fatima, before we end, can we go over a question that I kind of was confused on?
Which one?
On the December 1st lecture, I think it's like the second to last page of like all his written work before the homework.
Oh yeah. So I'm on the second to last page. Which one is it? Because this is just enols and ketones.
I think it was the last one. Is there any way you could pull it up, or maybe I could pull it up as well?
Because I have it open, but not on my iPad. There's a pathway one. Is that what you're talking about?
I think. Hold on.
This is the last page, has pathways. A and B.
Oh, actually, no. It's page 11. So yeah. So it's
okay. It's retrosynthesis.
Yeah.
So which one?
The first one from the second page.
Okay. Yeah, that's a good idea. So, here we have triple bonds, 2 carbons. So I'm just gonna start by writing a little list of things that I'm noticing about this. What's one of the most craziest things that you see in this final product? What's the most interesting thing that you see here that we need to pay attention to? What might be alerting you, obviously, is this functional group of the epoxidation kind of. So we know that there must have been epoxidation of some sort. And what else? It's trans. That's interesting. And we've added carbons. Right? Because if you look at this, this has 1 carbon, 2 carbons. This has 1, 2, 3, 4. So we've added 2 carbons. So so epoxidation, we don't know how to do epoxidation with a triple bond. So epoxidation comes from a double bond. So for epoxidation, you can do whatever you want. I'm just going to give this. Anything with the CO3H will be fine, and he'll accept that. And I just like writing that one. So this would come from a trans double bond, would make that, right? Is this making sense? I just want to make sure that I'm explaining this in a way where you understand it. What was the part that confused you the most when you looked at it?
Yeah, I actually got through the whole thing, but it was the last part where I wasn't sure how he got CH3 in the CO3H. But now we
This
kind of,
is, yeah, right. It's starting to ring a bell. This is from exam 2,
yeah. Mhm.
epoxidation, right? So that's that step. But let's just finish this off because we have like 2 more minutes and we can do this real quick. How to get from how to add to so how do we get a trans double bond? This could have easily come from a triple bond like this. And what do we do to get trans? We have to use a dissolving metal. So NaNH3 would work. And then how to kind of get from here to here, we'd have to substitute 1 carbon twice. We'd have to substitute 1 carbon onto the left, 1 carbon onto the right? So there's this 1 extra carbon here, 1 extra carbon here. So +1 on the right, +1 on the left. So what we do is we do Na, NH2, NH3, and then carbon with a leaving group, halide bromine, or chlorine, that would be fine. So then we get triple bonds with a carbon, and do that one more time. Na, NH2, NH3, and a primary halide with 1 carbon, and that'll substitute onto the other side. All right. Any questions about this retrosynthesis? So something that I guess now that we've seen a few patterns, I can kind of explain something. So if you see epoxidation, you know it must involve what? Melissa. If we see epoxidation, what reaction must it have involved?
I'm not sure.
Well, it's CO3, which what I basically
Oh,
talked about
oh,
here.
yes.
That's kind of what I should have done an example first. So I'm just going to do like a little mini list. Now, if we see something with a double bond, what could this have come from? What might be a nice reaction to use here? Anyone want to volunteer? If we see a double bond on its own like this, and I'm going to run through some examples. If we have a double bond but with an OH, if we have just an OH, right? So let's just do some like quick reactions real quick to see what could have given us what is a good thing to get a ketone on its own. Okay, this could have involved an enol that became a ketone. So I'm just going to write an enol here. So an enol reaction would be H2O, H2 SO4, and HgSO4. So that's an enol reaction. Or it could have involved a double bond with O3, H2O2, right? That's something to keep in mind. It could definitely come up on the final because we're going to do exam 2 on there. A double bond would give you a ketone alone. This could only have come from one thing. What is it? Any volunteers?
Ozonolysis.
Ozonolysis with a triple bond. So O3 and H2O2, and this must have been with a triple bond before. Anyone have any ideas about this one? OH standing on its own. There's 2 options.
Could you make it a double bond and use a mark rule?
Yeah. So it could have come from a double bond with mark. So or anti-mark. Or no, it couldn't have been anti-mark. So no, let me just make it because I can't remember that reaction now. Okay. So this must have been maybe like a double bond with anti-mark. Or yeah, so that would be No. Sorry, I'm just going to change this one more time. So this could be with B2H6 H2O2 with a double bond. And the double bond would be like this. Or it could be from what was the other thing I was thinking of? Actually, I think that's the only option. Because it can't have been from a enol. Sorry, it couldn't have been from, it couldn't have been a ketone to an enol because that reaction involves this. Let's see if we saw this. What would this be? What's the reaction that this came from? This is a OH with a double bond, so it must have been H2O, H2SO. 4H. Look at this one. That is similar to this one. So HgSO4 and H2SO4 and H2O, those can produce both an enol or ketone form. So you can use that reaction for both examples. Any last ideas that we should add to this list? It could be much longer. We could talk about adding carbons, taking away carbons, all kinds of stuff, but I think this is mostly, you know, if you see a trans double bond, then it must have been NaNH3 or LiNH3. If you see a cis double bond, it must have been Lindlar. Right. So these are just some tips for your retrosynthesis. For the last step, if you get that, you can kind of start rolling from there. Okay, so I'm gonna end this session for today, and I'll see you guys on Sunday. On Sunday, we'll go over December 3rd. Something that I left open for you guys is this retrosynthesis right here. So if you guys want, you're free to do this retrosynthesis and send me your answer. Wait, didn't I put a retrosynthesis there? This one. You guys are free to try this one out and send me your answer if you want to practice. This one's a little bit more involved, and I can send you some more retrosynthesis questions as well if you want. If you guys want, I could make a document of some retrosynthesis that I make up that are like a little bit more complicated, and they'll take like a little bit more, understanding of the material, but they'll be good practice, because if you practice with something harder than what he's going to give you, you're going to do great. All right. Okay, I'll see you guys on Sunday then. Have a good weekend.
Thank you so much, Fatima.
Thank you guys for coming.
Bye-bye.